Hello everyone. Today I would like to give you a lesson on the topic altitude of a triangle, perpendiculars. Before you start watching this video, don't forget to like my video and subscribe to my channel. I will be very grateful to you for this. The height of a triangle can also be found not only in textbooks. Here is where it is found in life. In physics, when calculating force projections onto a plane, or in problems with the center of mass of a triangular plate. In sports and games, for example, when designing ball trajectories or marking the playing field, triangles on a football field, volleyball. An altitude of a triangle is a perpendicular drawn from a vertex of the triangle to the line that contains the opposite side. Notice the three different triangles. The first triangle, ABC, is an acute triangle, and therefore the altitude, this red line, lies inside the triangle itself. The second triangle, also labeled ABC, is a right-angled triangle. In this case, the altitude coincides with one of the legs, that is, with one of the sides of the triangle. The third figure is a triangle ABC that is obtuse. I want to highlight its obtuse angle. Here it is. This angle is greater than 90 degrees, so the altitude, AD, is drawn to the extension of side BC. Sometimes there is a theoretical question. Does the altitude always belong to the triangle itself? Not always. Here is the last case where the altitude does not lie inside the triangle, but is drawn to the extension of side BC. Let's find out the theorem about three perpendiculars, abbreviated TTP. A line drawn in a plane through the base of an inclined plane perpendicular to its projection onto that plane is perpendicular to the inclined plane itself. From this figure, we can see that AH is perpendicular to MH, MH is perpendicular to M, and AM is perpendicular to M. We won't need this theorem in this video lesson, but believe me, we will definitely need it in the future. We can prove this theorem very easy. We are given that A belongs to the alpha plane. A is perpendicular to OA, SO is perpendicular to the alpha plane. We need to prove that AA is perpendicular to SA. From point A, we set aside equal segments. AM equals AN. We connect points M and N with points O and S. In triangle MON, OA is both an altitude and a median. This triangle is isosceles. OM equals ON. Right-angled triangles SOM and SNO are equal in two legs. From the equality of the triangles, it follows that SM equals SN, and SA is the median of the isosceles triangle MSN. Therefore, SA is also the altitude of this triangle, that is, SA is perpendicular to MN. We have proved this theorem. The center of the circumcircle around a triangle lies at the intersection of the median perpendiculars drawn to the sides of the triangle. It's very important to remember. Now, let's move to the problems. Problem 1. In the figure, an isosceles triangle ABC is shown, where AB equals BC. AD is its altitude. It is drawn to the extension of side BC. The angle BAD equals 16 degrees. We need to find the measures of the angle ABD. Let's begin working. Solution. According to the condition, triangle ADB is right-angled. Why? Because AD is the altitude. You must always focus your attention exactly on the figure you are working with. Right now, we are working with this right-angled triangle. We can now find angle B. I highlight it in red and mark it with X. But how do we find X? We know that the sum of the angles in a triangle is 180 degrees. Therefore, I make an equation to find X. Adding all its angles, 16 degrees, 90 degrees, and X, must give, in sum, 180 degrees. Thus, X equals 180 degrees minus 106 degrees equals 74 degrees. That is our answer. Now, the same condition, but punct 2. We need to find the angle DAC. Read carefully. From the previous point, we know that the angle ABD is 74 degrees. I've already marked it in blue. Now we can find the angle ABC. Adjacent to it, don't forget about adjacent angles, so they are adjacent in sum 180 degrees. Therefore, the angle ABC will be 106. I'll mark it in yellow. And then we look at the triangle ABC. By condition, it is isosceles. So how can we find the angle BAC, which in turn will be equal to the angle BCA? When we work with isosceles triangles, then our two angles, BAC in BCA, are equal. How do we find their degree measure? These two angles plus this one add up to 180 degrees. Therefore, to find one of these, we need to subtract this one from 180 and divide by 2. Here's how it's done. So, the angle BAC is 37 degrees. We're asked about this one. I'm highlighting it in red, angle DAC. It's made up of two angles. So we add 16 plus 37 is 53 degrees. That is our answer. So, if you understood everything today, I would give you Subaru 4x4 as a gift. If you are worried or excited because you did not understand something, no problem. Watch this video again slowly. Never give up. And I wish you to understand it as soon as possible. Bye!